When installing ground rods at light poles, it's important to follow the guidelines set by the National Electrical Code and any specific requirements from the authority having jurisdiction. While the NEC doesn't generally require ground rods at every light pole, local regulations can vary, so always check with your AHJ. Regarding the placement of the ground rod, it should be positioned inside the form hole, ensuring it makes direct contact with the soil. The purpose of a ground rod is to provide a low resistance path to the earth, and this is only achieved when the rod is in good contact with the surrounding soil. The National Electrical Code specifies that ground rods must be at least 8 feet long. With a 10-foot excavation hole, ensure that the rod is installed at least 8 feet deep. It is crucial that the ground rod has direct contact with the soil. Do not encase the entire rod in concrete, as concrete is not a good conductor of electricity and will compromise the rod's ability to function properly. The installation procedure involves several steps. Firstly, position the ground rod inside the form hole. Secondly, fill the hole with concrete, making sure the rod is securely embedded within the concrete. Thirdly, allow the concrete to cure completely according to the manufacturer's instructions. Fourthly, connect the ground rod to the grounding system using a grounding conductor of appropriate size and material as determined by the NEC. Always consult with the AHJ for any specific requirements or local regulations that may apply to ground rod installations at light poles in your area. Ground rods should be regularly inspected and maintained to ensure they are functioning properly. This includes checking for corrosion, damage, and proper connection to the grounding system. The National Electrical Code provides detailed information on grounding and bonding requirements in Article 250. It covers the purpose of grounding, which is to limit voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines, and to stabilize voltage to earth during normal operation. The NEC also outlines the requirements for grounding electrode systems, including the types of electrodes that are permitted, their size, and installation methods. Common grounding electrodes include metal underground water pipes, metal frames of buildings, concrete encased electrodes, and ground rods. When using ground rods, the NEC specifies that they must be at least 8 feet in length and made of specific materials, such as copper or galvanized steel. The code also addresses the spacing between ground rods when multiple rods are used. Typically, a minimum spacing of 6 feet is required to avoid overlapping of their effective grounding zones. The grounding electrode conductor, which connects the ground rod to the electrical system's grounding bus, must be size appropriately based on the size of the service entrance conductors. Table 250.66 in the NEC provides guidance on selecting the correct size of the grounding electrode conductor. In addition to grounding electrodes, bonding is another important aspect of electrical safety. Bonding involves connecting non-current carrying metal parts of the electrical system together to create a low impedance path for fault current. This helps to ensure that overcurrent protective devices such as circuit breakers and fuses will operate quickly to clear fault and prevent electrical shock hazards. The NEC provides detailed requirements for bonding in Article 250, including the types of bonding conductors that are permitted, their size, and installation methods. Common bonding applications include bonding metal conduits, metal enclosures, and metal water pipes. Ground fault circuit interrupters, or GFCIs, are another important safety device that can help to prevent electrical shock hazards. GFCIs are designed to detect small amounts of current leakage to ground and quickly interrupt the circuit, preventing a potentially fatal shock. The NEC requires GFCIs to be installed in specific locations, such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of electrical shock. Regular testing of GFCIs is recommended to ensure they are functioning properly. Electrical safety is a critical concern, and it is essential to follow the requirements of the NEC and any local regulations to ensure a safe electrical installation. When working with electricity, always take precautions to protect yourself from electrical shock hazards. This includes wearing appropriate personal protective equipment such as gloves and safety glasses, and using insulated tools. If you are not qualified to perform electrical work, it is always best to hire a licensed electrician. Remember to disconnect the power supply before working on any electrical equipment or wiring. Always use a voltage tester to verify that the power is off before touching any wires or component. Never work on electrical equipment in wet or damp conditions. Be aware of the location of overhead power lines and maintain a safe distance. If you see any signs of electrical hazards, such as frayed wires, broken outlets, or sparking equipment, report them immediately to a qualified electrician. Regular electrical inspections can help to identify potential hazards and ensure that your electrical system is in good working order. By following these safety guidelines and the requirements of the NEC, you can help to prevent electrical accidents and ensure a safe electrical environment. When installing a ground rod, it is important to select the right type of rod for the soil conditions. Copper-clad steel rods are commonly used because they provide good corrosion resistance and conductivity. Galvanized steel rods are another option, but they may not last as long in corrosive soils. The diameter of the ground rod also affects its performance. A larger diameter rod will have a lower resistance to ground than a smaller diameter rod. The NEC specifies minimum diameter requirements for ground rods based on the material they are made of. The depth of the ground rod is another important factor to consider. The deeper the rod is driven into the ground, the lower its resistance to ground will be. The NEC requires ground rods to be driven at least 8 feet deep, but in some cases, it may be necessary to drive them deeper to achieve the desired resistance. The soil conditions also affect the resistance of the ground rod. Sandy soils tend to have a higher resistance than clay soils. If the soil is very dry or rocky, it may be difficult to achieve a low resistance ground. In these cases, it may be necessary to use multiple ground rods or to use a soil conditioning agent to improve the conductivity of the soil. The connection between the ground rod and the grounding electrode conductor must be made using a listed connector. The connector must be suitable for direct burial and must be compatible with the materials of the ground rod and the grounding electrode conductor. The connection should be made above ground level to prevent corrosion. After the ground rod is installed, its resistance to ground should be measured using a ground resistance tester. The tester sends a current through the ground rod and measures the voltage drop. The resistance is then calculated using Ohm's law. The NEC does not specify a maximum resistance value for ground rods, but it is generally recommended that the resistance be no more than 25 ohms. If the resistance is higher than 25 ohms, additional ground rods should be installed until the desired resistance is achieved. The grounding electrode system should be inspected regularly to ensure that it is in good working order. The ground rods and connections should be checked for corrosion and damage. The resistance to ground should be measured periodically to ensure that it has not increased. If any problems are found, they should be corrected immediately. Proper grounding is essential for electrical safety. A properly installed and maintained grounding system will help to protect people and equipment from electrical shock and damage. It will also help to reduce the risk of fire caused by electrical faults. Therefore, it is important to follow the requirements of the NEC and any local regulations when installing and maintaining a grounding system. Always consult with a qualified electrician if you have any questions or concerns about grounding. Ground rods are typically made of copper-clad steel or galvanized steel. Copper-clad steel rods are more resistant to corrosion than galvanized steel rods, but they are also more expensive. The size of the ground rod depends on the size of the electrical service. The NEC provides tables that specify the minimum size of the ground rod based on the size of the service entrance conductors. Ground rods must be driven into the ground so that at least 8 feet of the rod is in contact with the soil. If the ground is rocky, the rod can be buried horizontally in a trench that is at least 30 inches deep. The top of the ground rod must be accessible for inspection and testing. The ground rod must be connected to the grounding electrode conductor with a listed connector. The connector must be made of a material that is compatible with the ground rod and the grounding electrode conductor. The grounding electrode conductor must be sized according to the NEC. The grounding electrode conductor must be run to the main electrical panel and connected to the grounding busbar. The grounding busbar is a metal bar that is used to connect all of the grounding conductors in the electrical system. The grounding busbar must be connected to the neutral busbar in the main electrical panel. The neutral busbar is a metal bar that is used to connect all of the neutral conductors in the electrical system. The neutral busbar must be connected to the service neutral conductor. The service neutral conductor is the conductor that carries the neutral current from the utility company to the electrical panel. The grounding system must be tested after it is installed to ensure that it is working properly. The test is performed using a ground resistance tester. The ground resistance tester measures the resistance between the ground rod and the earth. The resistance should be less than 25 ohms. If the resistance is greater than 25 ohms, additional ground rods must be installed. The grounding system must be inspected periodically to ensure that it is still working properly. The inspection should include checking the ground rods for corrosion and damage, checking the connectors for tightness, and testing the resistance to ground. If any problems are found, they must be corrected immediately. Grounding is an important part of electrical safety. A properly installed and maintained grounding system will protect people and equipment from electrical shock and damage. In addition to the points already covered, here's some extra information related to grounding light poles. When installing ground rods for light poles, consider the soil resistivity. High soil resistivity can significantly impact the effectiveness of the grounding system. Soil resistivity is a measure of how well the soil conducts electricity. It is affected by factors such as moisture content, temperature, and the types of minerals present in the soil. If the soil resistivity is high, it may be necessary to install multiple ground rods or to use a ground-enhancing compound to improve the conductivity of the soil. Ground-enhancing compounds are materials that are designed to reduce the resistance of the soil. They are typically made of a mixture of chemicals that absorb moisture and improve the contact between the ground rod and the soil. When using ground-enhancing compounds, it is important to follow the manufacturer's instructions carefully. Another important consideration when installing ground rods for light poles is the proximity to other underground utilities. Before digging, it is essential to contact the local utility companies to locate any underground cables, pipes, or other facilities. This will help to prevent damage to these facilities and ensure the safety of the workers. The depth of the ground rod is also important. The deeper the ground rod is installed, the lower the resistance to ground will be. However, it is also important to consider the depth of the frost line in the area. The frost line is the depth to which the ground freezes in the winter. If the ground rod is installed above the frost line, it may be heaved out of the ground by the freezing and thawing of the soil. In areas with deep frost lines, it may be necessary to install the ground rod below the frost line to prevent this from happening. The type of light pole being installed can also affect the grounding requirements. Metal light poles must be grounded to protect people from electrical shock. Non-metal light poles do not need to be grounded, but the electrical equipment inside the pole must be grounded. The grounding conductor for a light pole must be sized according to the NEC. The size of the grounding conductor depends on the size of the circuit that supplies power to the light pole. The grounding conductor must be connected to the ground rod with a listed connector. The connector must be made of a material that is compatible with the ground rod and the grounding conductor. The connection must be protected from corrosion. The grounding system for a light pole should be inspected regularly to ensure that it is working properly. The inspection should include checking the ground rod for corrosion and damage, checking the connectors for tightness, and testing the resistance to ground. If any problems are found, they should be corrected immediately.